Hi there, my name is Dave. I go by the online name of Dave Makes Stuff, and I make a lot of things with nTopology. So I wanted to show you this fun little project. It's a seasonal project. I just did recently a Halloween project. It's a Spiderweb generator. And this, as you can see up here, is a custom block for making a spiderweb because I had the option of or I created the option later for making some batch processing so you can make hundreds and hundreds of different spider webs feeding through the different, cycling through the different parameters that I've set up here. So I will go through that in more detail. Just wanted you to know up front. So what this ultimately makes is all sorts of spider webs. So let me just tell you a little bit more about where that's going to end up. This tutorial and others like it will be posted on the nTop education community site. For those of you that don't know about nTopology, I encourage you to go to ntop.com and you can read a little bit more about it here. So nTopology is it's an application for more advanced engineering tasks. I really like to use it for artistic and creative purposes, and but a lot of the things that I do use techniques that I think you might find helpful for more sophisticated applications. So that is why I share them here. All of these designs are posted for free. The STLs that I create, the spiderwebs are posted for free on my thangs.com profile, and you can download 250 unique spiderwebs from here. That's over 1.5 gigabytes worth of spiderwebs. So if you don't want to, or if you're not able to come in and generate your own spiderwebs using nTop, you can download pretty much any type of spiderweb that you might need for your Halloween season. So let's get into how this works. I'm just going to delete the title there, and I'm going to leave this spiderweb. So this is a completed spiderweb here, and let's just go through all of the different parameters here. So the first parameter is just the target diameter. So, and that's in millimeters. This is a 250 millimeter diameter spiderweb, and that's going from just the web part to the other side of the web part here. The number of sections is how it's sectioned off here, so you can count them. There's 16 sections in this particular spiderweb. Approximate strand separation is what this value is, and 10 looks about right for most spiderwebs. So that is the approximate separation between the strands here. And I say approximate because, as you can see, the spider webs are, it's an expanding spiral here. So the strands are closer together near the center, and then they get wider apart at the outside. And that is something that I learned about spider webs, is that my initial spider webs were made just using an Archimedean spiral. So Archimedean spiral is where the web strands are a set distance apart, and that does absolutely not look like a spider web. So part of what I had to build into this was an expansion coefficient that would expand the spider web on the as it stretched outward. This section here, the points per section, just refers to the number of reference points that are generated to create this curve. So 10 seems like a good number. If you needed a more high resolution curve here, then you might need more. Any less than that, and the curve sort of breaks down a little bit. But for the most part, you can leave that at 10. Inner start from origin. If you zoom in really close here, this you can't quite see it here, but this spiral actually starts right at the origin because it's as you can see, 0 millimeters from the origin. If you wanted to create a little bit more open space in the middle, you could set that a few millimeters to the side, and then the spiral would start not quite at the origin, and maybe you wouldn't get quite as much dense form there. The thickness is the diameter of each of the strands, so they are 2 millimeters thick. The support overshoot. You can see these radial strands, the support strands that come out here. They this is the amount that they overshoot from the web there. I didn't want them ending right at the web, just in case people wanted to use them to connect onto something. So that's approximately 10 millimeters that they overshoot. The maximum sag is set at 5 millimeters. So to sag, you can see that each of these, this isn't a straight sort of circular kind of spiral, nor are they straight strands in here. There's actually a little bit of a sag that goes in between, and we'll talk about that later. But that's actually a sine wave, so it's dipping down, and then there's a way that I modified that. But the that's the amount of sag from sort of a default of a circle to a sine wave that is the amplitude of the sine wave that sags down a little bit. And you can see also that if that was set at 5 millimeters for the whole place, it would just get really crazy down here in the middle where everything's quite small and tight. So that also varies as you go from the center outwards. At the very center, there is no sag, and then it gradually increases so that it's these outer strands that have 5 centimeters as the amplitude of that, or sorry, 5 millimeters is the amplitude of that sine wave that creates the sag there. So those are all the input variables, and so the point that I made earlier was once you have input variables set up like that for the different parameters, and you turn this into a custom block, when you import this custom block into another instance of nTopology, and say I create a list of values going from 50 to 250 in increments of 5, and I put that list in this target diameter place, that would actually create however many different spider webs in those increments. So it would create a 50 millimeter diameter spider web, a 55, a 60, and so you can vary all of these parameters and of course all the multiple permutations of those different parameters. So it's pretty infinite what you can do with this. Really more than you'd ever want to do with a spider web, but that's besides the point. This is a technical challenge. So let me just go down here and show you these. So when you're doing these curves, any curve that you're doing in nTopology is created using reference points. So these are all the reference points that are created using the inputs and the algorithms that I'll go through in a minute, and then those are the points that you then put the curve on top, and that curve is thickened and so on and so forth. So the top is the input, and then I have a section here. Well, these are just the samples, the sample spider web there. I won't go into a lot of details about these dependent variables, but these are just the values that are calculated from these input variables. So we have the number of spirals. In this case, I have a 250 millimeter diameter spiral with 10 millimeters between each strand. So this calculates that we're going to have 25 spirals. Right here, the number of sag periods. So that, if you can imagine that these are, the sags are actually a sine wave. The original sine wave would dip down here, and then it would actually dip up there. So it's actually a full period of that sine wave is actually 2 segments. So for this purposes, for the calculations right here, this is 16 segments, but for the purposes of calculating the sine wave, it's calculated as 8 periods to go around fully. The base radius, I won't go into a lot of the details of the math behind this, but basically it has to do with the fact that the distance between the strands expands as you go out. So the base radius would be sort of your basic Archimedean spiral that would not look like a spider web at all, and then I've created an expansion coefficient, and it's calculated so that with this base radius and using that expansion coefficient, I can show you what that list looks like. So it just multiplies every point by an expansion coefficient. The very center point is moved by 1, stays in the same place, and every point out from that moves radially out by this expansion coefficient, so that by the time you get to the end here, it's actually doubled. Don't need to go into the details of that. But also just to keep in mind here as we're going through these, the construction of the web, this is all done in polar coordinates. So as I'm setting these up, I'm setting up the values for r for the radius, and then so polar coordinates are derived from r, and then the theta, which is the angle value of those points. So everything here is done in polar coordinates, and then that is converted. So just moving down here, we've got the web that expands outwards, just a few other pieces that will come in the calculations. So 9,000 degrees, this whole thing by the time it spirals around 25 times, that's 9,000 degrees. I use degrees. You could do the same in radians. I just find it a little bit easier for my non-mathematical brain to work in degrees for this. Total sections, of course, spiraling around 25 times, times 16, there's 20 sections. So here we kind of get to the plotting piece of things. So these are all the polar coordinates. So theta, this is just the angles for every consecutive point. So the first one is 0, then the angle moves up by, in this case, 4.5 degrees for every point is moved along, and that just continues for something like 9,000 degrees. The base R values, that's calculated just an Archimedes spiral that would be small, and all the strand length would be different. This expanded R values uses those base R values and multiplies by the expansion coefficient. So this is what gives the full spider web. It's just a spiral at that point. And then this right here is these are the values that add the wave to it. So right here you can see I'm using a sine wave, but like I mentioned earlier, a sine wave would actually weave back and forth. I don't want that, so I take the absolute value of the sine wave. That would bulge out. I don't want it bulging out, so I multiply it by -1, and then I get the bulges in. Down here is the set of values, the list of values that make it so that the maximum sag at the start is 0 at the very center there, and then we're working out to the maximum sag value, which is 5 millimeters, and that just creates a list of a sequence between those bounds that is used to calculate the amplitude of that, or to affect the amplitude of that wave component there. And at the very bottom of the polar coordinates here, I have the R wave. So these are the R values that are then used to convert to Cartesian. So there's our theta values, there's our R values, and then the conversion to X and Y points is just using your trigonomic expressions there, and that gives us all of these points here when I plug in the X and the Y. And of course, in this instance, the Z just stays at 0 because this is just a planar spider web. If you wanted to get really fancy, you could add some Z values in there. Would be a fairly complicated spider web. And then all of those points are then used to guide the creation of a curve. And once you have that curve, we can go down here to the thickening section. So this right here, this section here creates the web strands. It's going to just take a little while. Sorry, the support strands that go out radially, and the full strand right here that takes the so this is a spiral strand here. It's a spiral web that takes the web curve there, and the curve turns it into a implicit line, which can then be thickened. So that is those thick spirals there. And then the web support strands, that's just those radial pieces, and that's just calculated by the diameter, the overshoot, and then of course the number of sections in the spider web. And then that is all Booleaned together, and that gives us the full spider web. So let me just turn off some of these. Let's turn off that right there. And for this project, the web curve takes a little while to calculate too. So let's just play around a little bit with this. So this is that target diameter of 250 millimeters. Let's just put that down to 100 millimeters. And it's just going through calculating, and it calculates the points fairly quickly. So you can see this is a smaller one. It's still The max sag value here is still 5 millimeters. That looks a little bit odd there when we have a spiral that small, but that may be what we're looking for. Just for the sake of experiment, let's just see what happens if we go up and just because I think that sag, it just looks like too much sag at the end there. So what happens if we put our sag value down to 3? So there you can see it comes up really quickly with just the reference points, and then that curve actually filled in quite quickly there. So this is 16. So you can see the little scallops. There's 16 of those. Let's just try changing that variable and see what happens. So let's put that right up to 24. So we're going to have a lot more sections. It's going to be a bit tighter. So there you can see just from the points, all these little scallops coming quite close together, and it takes a lot longer because, of course, when you increase the number of sections, you increase the total number of points, and then the curve is calculated over those points. So it takes a little bit longer to do that. But there you have it. That's the basics of my Spiderweb generator, and I'm going to now go to the program where I use this as a custom block, and I will show you how I use this custom block to generate multiple models of the spiderweb with the ranges cycling through these different parameters. So here's the next section of this project. I've now opened a notebook called Spiderweb Batch Processing. So if you look down here further on the notebook, you can see that I've imported the custom block Spiderweb. So that's what we created previously, and you can see the familiar inputs here. There's target diameter, number of sections, approximate strand separation. Those are ones that I've set up some different input values for. All of these ones stay the same: points per section, inner start from origin, thickness, support overshoot, and maximum sag. So you could change those, but for the purposes of this project, I just wanted to stick with modifying these ones right here. So this is where we really see the power of these custom blocks and using them in your projects. Within one notebook, you cannot have lists of lists. So I cannot create a list of multiple multiple lists of points, which is what makes up the spiderwebs. You can't do that in a single notebook. But if you use this custom block process, that's a way to kind of get around that. So looking up here, I've created the smallest diameter. I've created input for the smallest diameter and the largest diameter, the number of sections, and the strand separation. So right down here, I create a sequence, and this is a sequence that runs from up here, the smallest diameter, which is 50, and down to the largest diameter of 25. So what this batch processing is going to do is it's going to cycle through this custom block, creating a spider web first with a diameter of 50 millimeters, and then of course these values here, 16 sections and that strand separation. Then it's going to go back and create another spiderweb, implicit body of a spiderweb for 60, 70, 80, and so on and so forth. So I have done that already. I have already processed this sequence here and created the implicit bodies of 21 spiderwebs ranging from 50 to 250 millimeters. And then I've put that list of implicit bodies to create a list of meshes. Some of them came up with a mesh error. I'm not too worried about that. They printed just fine, but this is fun. Watch what happens here. There is the 21 different spiderwebs ranging from 50 to 250. So that's them all together, but we can pull that out here, and we can see we can take these chips and we can drag them in. So this first one is going to be the 50 millimeter diameter spiderweb, kind of tiny. Let's take one from the middle here. So that one's a little bit bigger there, and then let's go to the very end. So this is going to be the 250 millimeter spiderweb. And if we zoom in on here, just for people who are thinking of printing this is a pretty nice high density mesh that you can certainly scale up if you are FDM printing, and that will also print fine with resin printing too. That's at 2 millimeters 2 millimeters diameter is the thickness of the strands. So that's pretty cool how you can make all those different the different meshes and cycle through the different variables. This is the part that I found really interesting to set up. It was just the first time that I was doing this, and this is just creating a batch processing for the saving and the naming of all of those meshes. So in here I have an input for the file location, so you would simply cut and paste the location on your computer that you would want them to go. And in here I'm just tagging on all the different variables that are being used to construct these meshes. So D values, that's the diameter values, and what I'm doing here is I'm making text from scalar, and this is a list. So this is a list of text values that I've pulled from the list of diameters. So you can see here it's just a text value 50, 60, 70, so on, and I'm tagging that onto the file location with the dash dia before, standing for diameter. So that will add onto the file location dash diameter 50, diameter 60, and so on and so forth. And here I am pulling, creating a text from the scalar value of the number of sections, which is just, in this case, 16. And I'm just attaching that onto the file name here with the delimiter of .sec, standing for sections. So that's going to add a section 16. I'm taking text from scalar for the strand separation, which in this case is 10 millimeters, and that tags it on there. And then adding on the value for span, so dash span. So this creates a file name with dash diameter, followed by dash section, dash span. And what this does creates a list. It's the same, the list with the same number of values as the number of meshes, so 21. This creates a list of 21 file pathways and matches them up and saves them. So this takes quite a while to run through, probably about 15 or 20 minutes, because of course you're creating all the implicit bodies, you're creating all the meshes. I have a slow computer, so I'm not going to do that. I'm not going to do that here, but it is, it's really powerful, and this is how I created my my 260 massive download of different permutations of Spiderwebs. It ended up coming to 1.5 gigabytes worth of Spiderwebs. I just did that by cycling through the different parameters here. So a lot of fun. You know, probably not a lot of application in real life here, but I hope you've learned something about how amazing nTopology is for creating complex curves and shapes using reference points, and how you can use algorithms and mathematical equations to create those patterns, and then you can parameterize them, and then once you start using the custom blocks, you can actually batch process and do some pretty high volume outputs with some pretty complicated shapes. So I hope you enjoy that. As I mentioned, this file will be available on the nTop community page for you to download. If you don't want to or can't go through the process of generating your own spiderwebs, there's, like I said, a ton of downloads of the spiderwebs on my Thangs page. And I hope you enjoyed. And please, feel free to leave comments on YouTube or my social media, and I will try my best to respond and walk you through. Have a lot of fun. This is Dave from Dave Makes Stuff.